In today's experiment, we're going to look at trying to calculate an actual equilibrium constant expressed in terms of concentration, looking at the molarity of solutions for the reaction between iron 3 plus thiocyanate, SCN minus 1, and forming a complex FeSCN with a 2 plus charge that has an orange to reddish color depending on the concentration that you're working with. In terms of this particular experiment, the iron 3 has also had some nitric acid added to it. And the reason for doing that is that it will prevent it from forming a reaction with hydroxide ions that are found in the aqueous environment that has a tendency to give it an orange color. So this will make it more of a colorless solution when we first start. And then all the color being produced is based on the complex that's being formed, the FeSCN 2 plus ion that's going to be produced. We need to know exact concentrations for this experiment so that we can relate those concentrations to what is the absorbance of light that's going to be created. The darker the color, the more the light is going to be absorbed. And we will also look at what particular wavelength we're going to be working with. You might recall this is a red-orange color. So if you remember the color wheel, the opposite of a reddish-orange color is blue. So it will absorb the most radiation for blue light. And that's why if we're using a colorimeter, which we are in this experiment, we're going to set the LED to be 470 nanometers, which is a blue LED. If we were using a spectrophotometer, we might be able to tweak this a little bit and go a little higher or a little bit lower and still get good data, but that's what we're going to be working with today. The solutions have been already prepared so that we can just try to go through this relatively quickly and collect the data. We're going to be mixing together various amounts of 0.002 molar concentrations of iron 3 with 0.002 molar SCN ions. And then that's going to end up producing our complex. As a comparison, we are going to take some of the SCN that we have, and we're going to add just an extreme amount of excess iron ions compared to the amount of SCN available. What this will do is it will stress the equilibrium system, and it will push the equilibrium to make more and more products to try to reestablish a balance between the products concentration divided by the concentration of the iron 3 times the SCN minus molarities. So that's the equilibrium expression that you're going to be working with. We're assuming that Beer's law is going to be applied here. And what that basically means is that the amount of absorption that you have of a particular colored solution is going to be dependent on taking a look at what the actual wavelength is that you're using. There's a constant called epsilon, Greek letter E, or molar absorptivity. So it's based on how much it actually absorbs at 470 nanometers for 1 molar concentration. You'll also have the path length, or the amount of solution that the light has to pass through in a straight line fashion. Sometimes if you're looking down into a solution, you're talking about the depth. In this experiment, we're going to be using 1 centimeter cuvettes. So that's going to be a constant in terms of our relationship. And then the third factor is the concentration, or the molarity of the solution that you're dealing with. So the absorbance is equal to that molar absorptivity constant multiplied by the path length, which is 1 centimeter. That's going to stay the same, multiplied by the concentration. So now we get absorbance going to be directly proportional to just the concentration in this case. Let's get started with looking at the reaction. I'm going to shift this over so that you can see the setup that I have here for our individual test tubes. The first reaction that I have here is going to be producing of the standard. Now the standard is in test tube number 5. This has just 2 milliliters of the 0.002 molar FeSCN inside it. And then what I'm going to do is I'm going to add to it 18 milliliters of iron as a 0.2. So this is a quite concentrated solution, and it's pushing the equilibrium to get more of the dark orange reddish product of the FeSCN that you have available. For each of these other test tubes, I have various amounts of FeSCN that's been added to it. In each case, there's 5 milliliters of 0.002 molar iron with either 2, 3, 4, or 5 milliliters of the FeSCN added to it. The amount of solution total is balanced in those cases where we don't have a total of 5 milliliters by adding some water to that setup. So in test tube number 1, what I have is 5 milliliters of the iron. That's going to be reacted together with 2 milliliters of the potassium thiocyanate, which produces our FeSCN, and then 3 milliliters of water. So this is test tube number 1. Test tube number 2 also has 5 milliliters of iron, but now we have 3 milliliters of the FeSCN with 2 milliliters of water. So you can see that there's 1 more milliliter of the FeSCN, and hopefully you can notice that the color is slightly darker. In the next one, I have, make sure I get it all in there, 4 milliliters of the FeSCN with 5 milliliters of the iron. So there's 1 milliliter of water. Now this looks like it's higher, but it's actually a skinnier test tube, so it's the same volume that we're working with in each case. And then the last one, test tube number 4, what we have is straight up 5 milliliters of the FeSCN combined together with 5 milliliters of the iron in that setup. So we go from the lightest color, which has only 2 milliliters of the FeSCN, to the one that has 5 milliliters of FeSCN, and then our standard, which should be the actual darkest value. Okay, I'm going to pause there for a moment while I set up my colorimeter for doing the next part. I'll be back in a moment.